Assalamualaikum and hi. This is part 3 video for chapter 6 air conditioning. In this video, I'm going to explain subtopic number 4 air conditioning properties. Air conditioning properties. Specific and relative humidity. So specific humidity is related to the human comfort and it is also related to the amount of water vapor in the air. And as already explained in the previous slide, in the air we have a content of water vapor and also dry air. So specific humidity is actually we calculate the actual amount of water vapor in the air, and it can be calculated from the mass, which is from this equation. Omega is the specific humidity. It is equal to mv divided by ma. Mv here is the mass of the water vapor divided by mass of the dry air, and it can be calculated from the equation of ideal gas law, which is equal to m equal to pv divided by rt. And omega we also can calculate from the pressure of the dry air and also pressure of the water vapor. And we know that the pressure of the air is equal to PA, which is the pressure of the dry air, plus pressure of the water vapor. And we can rearrange this equation to be something like this. And it is the amount of water vapor in the dry air, in the air. And we also call it as the moisture content. Whenever the moisture content is higher, omega also will be higher. Another important thing is the relative humidity, which is the it's influence the comfort level of the environment, and it can be calculated from this equation. Psi is equal to mv divided by mg. Mv here is the same as the specific humidity, which is the mass of the water vapor, content of water vapor in the air, and mg is the maximum of moisture the air can hold at the same temperature, meaning that at a certain temperature the air can hold certain amount of water vapor in it. And it also mv can be calculated from the ideal gas law, and we also can calculate psi by using the pressure of the water vapor and also pressure at the saturated. And the value of relative humidity, the maximum value of relative humidity is 1, and the lowest value of relative humidity at the surrounding is 0. And if the value is 0, meaning that it is a dry air with no moisture content. And if the relative humidity is 1, meaning that the air is at saturated with moisture, and if you add more, it will be condensed, then to be water. And let's say we use the equation of the specific humidity, and this condition is at the saturated air condition, psi equal to 1, and from the omega, which is the specific humidity equation, omega equal to 0.622 pg divided by p minus pg. As you can see here, the value of pv here will change into pg because the pressure is at the saturated air condition, and PV is equal to PG, meaning that at the saturated air condition, the PV, which is the pressure of the water vapor in the air, is equal to the saturated pressure. And from this equation, as you can see here, the one which I put in the blue dotted rectangular, and omega equal to 0.622 PV and divided by P minus PV, we can find the relation between these two based on these two equations. Maximum moisture carrying capacity of air. As you can see, this is the temperature versus the maximum water content. And as you can see here, this is the range of air conditioning temperature, which is from minus 10 degrees Celsius to 50 degrees Celsius. And from this table, you can see that the amount of water content is increasing with the increasing of the temperature. So meaning that the larger the temperature, the higher the air can hold the water content inside of it. And I got this table from this link. Total enthalpy atmospheric air. So as we all know, the atmospheric air is a mixture of the water vapor and also dry air. So to calculate the enthalpy of the atmospheric air, we should consider both, which is the enthalpy of the dry air and also enthalpy of the water vapor. And as we all know, we can calculate the enthalpy from this equation, which is the enthalpy is equal to m, which is the mass of the component times the specific enthalpy. And we can expand this equation to be something like this, which is the ma is the mass of the dry air and mv is the mass of the water vapor. And we can divide by the mass of the dry air to get this equation. And as you can see, mv divided by ma is equal to omega, which I already showed in the previous slide. And we can simplify this equation to be he plus omega hv. And as we all know, hv, which is the enthalpy of the water vapor, is equal to the value of hg, which I already explained in the previous slide, where the ideal gas, the value of enthalpy is equal to the enthalpy of the saturated vapor line. So we can rearrange and replace the equation to be H equal to HA plus omega times Hg. So this is the enthalpy of the atmospheric air, which is the combination of the water vapor and also dry air. Air conditioning temperatures. So this is the temperature range of air conditioning system, which is from minus 10 degrees Celsius to 50 degrees Celsius. And in the air conditioning system, we should know three type of temperature, which is the dry bulb temperature, the ordinary temperature of the atmospheric air, and another one is the wet bulb temperature. It is the temperature which is measured by a thermometer whose bulb is covered with a cotton wick saturated with water and to blow air over the wick. So this is the example of the wet bulb temperature, as you can see here. So this is the ordinary thermometer and it's being covered by a wet wick or cotton wick, and the temperature measured by this thermometer, which is being covered by this wick, is the wet bulb temperature. And another one is the dew point temperature, the temperature at which condensation begins when the air is cool at constant pressure. As you can see, the dew point temperature is equal at the saturated temperature as constant pressure. Looking at this TS diagram here, this is the TS diagram. And as you can see here, this is the saturated vapor line and this is the saturated liquid line. And let's say initially the air temperature or the dry bulb temperature is T1, and then the environment is being cooled down at a constant pressure PV here, following by this constant pressure. And this pink line here actually is the constant pressure line. So whenever the air is cooled down from T1 at constant pressure PV, then the temperature will goes down until it reach or it touch the saturated vapor line, and this is where condensation start to happen, and this is being called as the dew point temperature. One example of the dew point temperature is whenever we how to say, the soda which are cold, and then we put it at the environment temperature, then suddenly water droplets start to appear at the soda can wall. So this is the phenomena of uh, the air being cooled at a constant pressure until it reach the dew point temperature. Specific humidity and relative humidity determination. So we as we look into the air conditioning system, we know that the specific humidity and relative humidity being used frequently, and we can measure. So we know that we can measure these two by based on this pressure and also temperature. So from the dew point temperature, which is from the previous slide, we know we can calculate both the specific humidity and also relative humidity. So let's say we know the dew point temperature, we know that the pressure of the saturated pressure. Then we can calculate the relative humidity and also the specific humidity. This way is simple, but it is not practical. to be used in the air conditioning system. And so there is another way of measuring these two quantity, which is from the adiabatic saturation process. Let's say we have a long channel. This is the long channel here. This is a long channel, and environment air, which is this unsaturated air, goes into this liquid water at state 1. We know that temperature 1, and this is a pool of water. Whenever this unsaturated air goes into this long channel, then the water will be evaporate, and it will increase the water content of this unsaturated air, and the output of this unsaturated air will be saturated air with 100% relative humidity, and the temperature will be slightly lower, and this temperature will be called as the adiabatic saturation temperature. And if you look at the TS diagram, this is the process that happen in this adiabatic saturation process, where we have this temperature of the state 2 at point 2 here, which is called as the adiabatic saturation temperature. Specific humidity and relative humidity determination adiabatic saturation process. Okay, so from the long insulated channel with the pool of water, so this is the long insulated channel, and this is the pool of water, and with the water makeup, which is liquid water at temperature T2. Let's say there is a unsaturated air, or the environment air at state 1 goes into this long channel with the T1, and some of the heat which is coming from the unsaturated air will evaporate the liquid water in the chamber, in the channel, and it will be evaporate the water vapor, and this water vapor that evaporate is equal to m dot f, and the output of this water or the air, it turned out to be saturated air with the 100% relative humidity, and this temperature at state 2 is called as adiabatic saturation temperature. So actually this process is used to determine the omega 1 by using adiabatic saturation process. From the mass balance equation, dry air of the air is constant. The mass of the dry air is constant throughout the process, and for the water vapor we have the mass flow rate at state 1 is plus mass flow rate of the fluid, and it is equal mass flow rate of the makeup water from this liquid water. As you can see here, this is the liquid water, and this is the additional mass from this process, and the output of it is uh, mass flow rate of water at state 2. So from the equation of omega, which is equal to mv divided by ma, we can replace this mass flow rate of water vapor to be mass of dry air times the omega 1, and plus the mass flow rate of water vapor, mass flow rate from the makeup water, and it is equal to mass flow rate of dry air times omega 2. And from the evaporation, which is the ma, which is the mass flow rate of dry air times omega 1 plus mass flow rate of the makeup water, mf, m dot f, and it is equal to mass flow rate of dry air times omega 2. And we can rearrange this equation to calculate the mass flow rate of the makeup water that being added into the unsaturated air before it goes out of the long insulated channel. Specific humidity and relative humidity determination adiabatic saturation process. So we already looked into the mass analysis. Now we look into the energy analysis. So this is the long insulated channel with a pool of water, and from the mass analysis we know that the rate of makeup water, which is the mf, is equal to the rate of evaporation water. So this here is the makeup water. So the rate of this makeup water is equal to this rate of evaporation process. So it is a steady flow process. So the energy from the energy balance equation, we know that Q dot is equal to 0, and work also equal to 0. So from this, the energy balance equation is energy in equal to energy out. So from the energy process, we know that this is some sort of mixing chamber. So we look into the enthalpy of the system, where mass of the air times the enthalpy at state 1, H1, plus m dot F times HF2 equal to m dot A times H2, which is this is the uh, at state 1, and this is at the uh, evaporation process, and this is the final or the state at stage 2. And from this equation, we can expand it to be something like this. From this equation, where m dot f equal to m dot a times in the bracket omega 2 minus omega 1, and we can input it into this equation, and we can divide it by ma, which is the mass flow rate of the air, and we can get this equation. And from this equation, we know that h is equal to ha plus omega h, and ha is equal to cpt, and we can use these two equation and put it into the simple equation and rearrange it. We can get omega 1 is equal to Cp times in the bracket T2 minus T1 plus omega 2 HFG divided by HG1 minus HF2. And you also can know the omega at state 2, which is this specific humidity at state 1 and specific humidity at state 2. So from these two equations, we know we can calculate the specific humidity at state 1 and specific humidity at state 2, provided we know that this temperature at state 1, we should measure as temperature at state 1, temperature at state 2, and also pressure at state 2. So from these two equations, we can calculate the specific humidity at state 1 and also specific humidity at state 2. Specific humidity and relative humidity determination, sling psychrometer. So we already looked into the adiabatic saturator, which is use the long insulated channel, where in the channel we have the evaporation process, and the exit of this long insulated channel is the saturated condition of the air. So it is not a practical approach, so we have a practical approach by using sling psychrometer. So the principle of the sling psychrometer is the same as the ordinary thermometer is covered with the wick, which are wet with the liquid water, so it can measure the wet bulb temperature. So for the sling psychrometer, as you can see in the figure, which labeled by the device, we have the wet bulb temperature and dry bulb temperature, and then we have the wet bulb thermometer, where it is being covered by a wick with wet with the liquid water. So the principle here is the dry bulb temperature will give the current air temperature, and whereas for the wet bulb temperature, wet bulb thermometer, which is covered by the wick, will measure the wet bulb thermometer. So the principle is when we swing this device, the wick will evaporate. Water at the wick will evaporate and cooling down the dry air in the environment. So it will measure the wet bulb temperature. Specific humidity and relative humidity. So this is the sling psychrometer, which actually the sling psychrometer use similar principle as the adiabatic saturation process. So let's say we have an ordinary thermometer which are covered with the wick and liquid water, and the unsaturated air will goes across this wick with the temperature air, T air, and we have a Q gain, which is heat gain, and the heat loss will be the water evaporate, which is the Q loss, and we have the slightly lower temperature of the water. So the difference in temperature is equal to T air minus T water. So Q gain is equal to Q loss, and from the wet bulb temperature, and here it will measure the wet bulb temperature, which is in general the wet bulb temperature and the adiabatic saturation temperature are not the same. However, for the air vapor mixture in the atmospheric pressure, the wet bulb temperature and the adiabatic saturation temperature is approximately equal. So from this equation, which we calculate or we derive from the previous slide, omega 1 is equal to Cp times in the bracket T2 minus T1 plus omega 2 HFG2 divided by Hg1 minus HF2. And omega 2, which is the relative specific humidity at state 2, is equal to 0.622 Pg2 divided by P2 minus Pg2. So from this equation, we know that this T1 is actually the dry bulb temperature and T2 is the wet bulb temperature, which both of this temperature we can measure by using this sling psychrometer. As you can see, we have this wet bulb temperature and also dry bulb temperature. So from this device alone, we can measure the specific humidity of the environment without using a complicated device, which is the adiabatic saturation process device. This is the end of part 3 for chapter 6. Thank you and hopefully you enjoy my video.